Precalc chapter 8 section 3. So we're going to look at geometric sequences. Kind of go through the same things like we did for arithmetic, just do it for geometric. So a geometric sequence, instead of having a common difference, these consecutive terms have a common ratio r. So instead of adding the same number every time, we're multiplying the same number every time, and that's what makes it geometric. So if we have our terms here, term 1, term 2, and term 3, and so forth, we can find those terms. So term 2 is the same thing as term 1 times the common ratio r. Term 3 can be found by doing the term 1 times r squared, 2 of those r values. And so we're multiplying the previous number by r, or multiplying the first term by one more r as we go along the pattern. To find our r value, we can take those consecutive terms and take like the second term divided by the first, or the third term divided by the second, or so forth, and then I'll find your common ratio r, what we're multiplying by. And so we're looking at a basic pattern. So like 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. That would be a geometric sequence. And so we're taking the first term times an r value of 2, the second term times another r value of 2. So the common ratio here of r would be 2. And so the form of this is just an exponential. Exponential is the function it relates to. And so the nth term of this example I'm doing here is going to be our starting value, so our first term is 1, times our r value 2 to the n minus 1 power. And this is a general rule for this rule. So a generic way would be writing it would be the nth term is always the first term times whatever your r is to the n minus 1. Now there's a relationship, and it's kind of written down here as well. There's a relationship that's always true here. So if we have the first term and we're trying to find the seventh term, this is going to be r to the 7 minus 1, or 6. So notice how this number, the first term, and the power of 6 always add to be the term you're finding. So we can actually alter this and say we're trying to find the 10th term, and we want to put the third term here. Instead of the first term, we're going to use the third term. Then it's going to be r to what power? It's going to be 7. The power of your r and the term number you're at always add to be the term number you're finding. And that's always works for this pattern. We did this back in exponential functions back in, I think it was chapter 3, when we were looking at, I think the problem was about the band about fish, and about how many fans they had. And so we kind of use a similar process using that knowledge of how this term number and the power always add to be the term you're finding. So let's go ahead and find the nth term of this pattern. So first thing I'm going to do is do 30 divided by 5 is 6. 180 divided by 30 is 6. So I find that the common ratio r is 6. So then my starting value is 5. So 5 times our common ratio 6 to the n minus 1 is the rule. So we want to find the 10th term in that. It's going to be 5 times 6 to the 9th power. So it's going to be a very big number. I'm just going to leave it like that. The next one here, whenever you have fractions and you're dealing with a sequence that has fractions, a lot of times I'll look at the numerator different than the denominator. So I just look at the denominator, 4 to 16, 16 to 64, 64 to 256. I'm multiplying by 4. So that bottom number, the denominator, is going to be our starting value 4 times our common ratio 4 to the n minus 1. So this is the denominator of this sequence. So the numerator just needs to alter signs, just positive, negative, positive, negative. So the first one want to be negative. So negative 1 to the power of always has to be an odd number. The first term is odd, so let's just have it be n. So if we have the first term, you're plugging 1 in for n, it's going to make that numerator negative. So this is the first term, we want that negative. The second term, we want this to be positive. So you plug in 2 for n, you have a negative 1 squared, which is positive. So here's a general rule for this pattern. So this is a more difficult. This is we're giving the 2 points, 2 terms. So the second term is negative 18. Let's say 0.2, negative 18. And we're also given the fifth term is 2/3. Now we don't know the common ratio for this, but we know that it's going to be geometric, so we can write the geometric form. And we don't know the first term either, so what we need to do is we need to use the terms we have. So I'm actually going to put the second term here, the second term instead of the first term, and then we also know the fifth term, so we're going to write the fifth term here. So I know the second term, I know the fifth term, so then I can find r, because I know that the term number and the power has to be 3, always add to be 5. So that relationship is very powerful here. So then I can plug in, the second term is -18, the fifth term is 2/3, and now I need to solve it for r. So I'd first multiply both sides by -1/18. So we do that, this reduces, the 2 and the 18 reduce to 9. So multiply across, I get -1/27 equals r cubed. And then we can cube root both sides. So cube root, when you cube root, you don't get the positive negative, you just get the value. So the cube root of a negative, cube root of a negative we can do. Cube root of a negative is negative, and cube root of 1/27 is 1/3. So there's our r value. So then I can use that and kind of the setup here. So I can still use the second term here, but now I know my r value. So I'm going to do the second term. I know the r value is -1/3 to the, I'm not going to make power yet. And I'm going to find, I'm trying to find these 6 terms. So the sixth term, so my power is going to be 2 plus 4 equals 6. And so now I can plug in my values. I know my second term is -18. -1/3 to the 4th power equals the 6th term. So you have to deal with the power first. So -1/3 to the 4th power is +1/81. And so then if I multiply there, I get a negative. And 9 goes into both of these numbers. So I have 2 and 9. So I get 2 9ths. There's the 6th term. Now you could have just kept dividing by -3 for each of these numbers and multiply by -1/3 to find them. And it's not too hard to go from this one to the next term, the 6th term, but I want to show you the algebraic way of finding that in case I wanted the 100th term. So the summation of a finite geometric sequence. So we have another formula for this, which is on your formula sheet. The summation of 1 to n values. So you can say like I equals 1 to n of our first term times r to the n minus 1, and really could write that the first term times r to the I minus 1, and this is just the notation, is going to equal the first term times 1 minus our common ratio to the nth power over 1 minus our common ratio. And this will find the summation of a finite geometric sequence. So in this example down here, we have n is 1 to n is 9, adding up all those terms for this pattern. So to find that, I need to know what the first term is, I need to know what the common ratio is, and I need to know what n is. Those are 3 values I need. The first term is always the number being multiplied, so it's like 1 times. And that's because if I plug a 1 in for n here, 1 minus 1 gives me a power of 0. Anything to the 0 power is 1, so 1 times its coefficient here would be, in this case, 1. The r value is the base, it's 2. And then our n value is how many terms we're going to add, so 1 to 9 is 9 numbers. And so you can plug it in the formula. So the first term is 1 times 1 minus 2 to the 9th power, all over 1 minus 2. So this is going to be really 1 minus 2 to the 9th, which is 512, all over -1. So then we have a negative 511, because 1 minus 512 over -1. So we get 511 as the summation for it. The sum of an infinite geometric series. Now this is the special case. Infinite geometric series, which means goes on forever and ever and ever. If we have a geometric sequence that's growing, so getting bigger and bigger and bigger, so it's going to be exponential. We can't find the summation of that because it's growing, it's getting bigger. But if we had a infinite sequence that's decreasing, so if we have a decay model here, we have a horizontal asymptote. And so this value is going to be approaching another number. And so we can actually find the summation because we'll say eventually we're going to be adding nothing because it's going to be so small because it's approaching that horizontal asymptote that we could add up all these numbers. So you can find an infinite geometric series when you have your pattern when r is less than 1. When the absolute value of r is less than 1, you can find an infinite geometric series. So that's the only time you can do that. So here, find the sum of the series. So the series is basically adding up an infinite geometric sequence. That's called a series. We need to check this number here. Our base is 2/3. So since our r value is 2/3, then yes, we can find a series. So to do that, we have another formula. The summation of 1 to infinity is just going to be the first term over 1 minus r. So it's actually an easier formula to deal with. So in this case, our first term is the number in front. So our first term is that 6 divided by 1 minus r. R is our fraction. So 1 minus 2/3. So it's going to be 6 divided by 1 minus 2/3 is 1/3. So I'm really going to be doing 6 times 3, or 18. So 18 would be the sum of this series.